At the moment, the robot isn't executing any commands. So we should add some test where the robot actually moves. If we take a simple case, we can change the test that we've got here so that the robot actually makes a movement. So we can call this test a simple command set, and we actually need to add a movement command, because at the moment the start position 0, 0 is good enough. So if we add just a simple move command moving north 1 position. Yep. And now we've got one command. We can have a null reporter, but we should change our test assert so that the Y location should be 1 above the starting position. We run the tests. Okay, and the test has failed. So the robot actually hasn't moved, and that's because the robot is not executing any commands. So we have to change the code so that we can pass the test and do the minimum changes possible, as always. So if we go to my execute commands, here we can loop through the movement commands that are contained in our command set. And here we can actually move the robot. And we can generate the method stub here. We can use a switch statement. Based on the direction. In the north case, east, south, and west. For north, we can update the position of the robot Y coordinate to a new position. In fact, no, we can't update the Y, we just create a new position with Y plus 1 coordinate. For the east, it'll be the original position, but X will be plus 1. For south, it's Y minus 1. And for west, it is X minus 1. We also have a requirement specification here we should look at. We should also test. But for the moment, I think we should just build F6 and then run our first test and see what happens. Yep, it runs okay, that's great. Okay, the requirement says that the robot will never be sent out of bounds. Okay. And actually that means it would never get a bad command that sends it out of bounds. Out of bounds being between minus 100,000 and plus 100,000, but it probably be safer for us to actually have a unit test or a control to make sure that this never happens. So let's create a test where we actually try to push the robot out of bounds. And if we copy this earlier test, and here we're going to run the robot with an illegal command set. And this command set will remove it out of bounds. We'll move it out of bounds. And the robot should, of course, remain within bounds. So we can start the robot, the initial position, right at the edge of the legal zone, which is, we can give it an x coordinate of 100,000 and a y coordinate of 100,000. And then if we move it to give it one movement command where we're moving it north by 1, which would take it outside of the bound zone. And afterwards we should check that the robot has not actually moved. So the x should be the same as the start position, and the y should also be the same as the start position. Okay, so if we build and run this test, oh, we've got a failure, and we see it's actually gone out of bounds. If we go to our execute commands, and here there's nothing to stop us actually, you can see, moving outside of the bounded zone. So we should do a control. And well, the expert pattern says it's the position really that knows about where its location is. So perhaps we should let the position validate itself or check itself. So we could create a validate method for the position. Now obviously there are many types of validations we can do or may want to do in the future. So this is an area of change, volatile area, and as such we need to take special care with sections of code that are likely to change. For example, we might want to pass a validator method to the location object via the enterprise pattern. But for the moment, we're just going to simply check if it goes out of the bounds. So we really just need to set it at the moment, send in some description of that bounding zone. And the validate method needs this information. So we need to describe the bounding zone, perhaps using the two corners of the bounding zone. So we can describe it as the bottom left corner, perhaps, of the bounded zone, bound bottom left, yep, corner, and of course another location which describes the top right corner. Right. Oh, we don't need to really have the types there. And now we need to we can pass these bounding corners into the constructor. But this will of course invalidate our existing tests, which we don't want to do. We don't want to change the code for existing tests if we can avoid it. So if we get the two locations, bottom left corner, top right bound, yep, and we add an internal field for this. Yes. Then, so to avoid making changes on our let's see, just check. Yeah, we got the naming correct. And we can generate our right, we need to take away the type. And then we can generate our method. Right, and of course if x is outside the bounds, we need to set it inside the bounds. And the same for the y coordinates. And we need to clean up our parameter names here. We can build. Okay, and as we said, we have invalidated our existing tests since they don't have any bounding information, and they don't need any bounding information either. So the easiest way to handle this is just to create a simpler constructor version, which doesn't have bounding information. And in this constructor, of course, the bounds corners will be null. So we can call our normal, or our more extended constructor with the null parameters. But since we can't do any error reporting here, we should really check in our validation method. So we only validate information we can validate. So we validate using the bottom left bound if we have the bottom left bound corner. And we only validate using the top right corner. If we have the top right corner. Okay, so now we can go back to our tests. And if we run our unit tests, okay, we've got a fail. We've got a fail. Because we're not actually sending in our bound corners where we need to. And actually here we're at the 100,000, so we only actually really need the top right corner bounding information for this test. So we can send a null for the bottom left corner. this would be 100,000 and 100,000, yeah. Oh, we're missing a null for the reporter rocks as well, but we need to have two nulls, yeah. Okay, if we can F6 and build and run our unit tests again. And we're still moving outside the bounds. What's wrong with the test? Still failing. Let's go to our declaration and go to our move robots. Seems to be fine. What about the validation method? If we check the validate position, okay, We validate when we validate here on Y, we're actually just changing the coordinate for X, so we we need to fix that. So we validate Y, we changed the coordinate Y. Okay, looks good. Build it again. Let's run our unit test again. And everything's running green, and it works. That's great. And now that we're actually moving the robot, we can actually test a bit more on the reporting. Instead of that basic null reporter test we had. So let's create a new test specifically to do that. Okay, if we copy this test. Okay, here we're going to run the command, run the robot with a simple command set. Just one move command. And the robot should report correctly. The location's cleaned. So here we've got, see we can, we just set the initial location. It's not really important. We move one space north. And we can set our bound information from, so this is 0, 0. Oh yeah, actually no, in our specification it was minus 100,000, minus 100,000. We need to add a reporter here. And I don't think our test reporter is enough. We need to create a real reporter class. At the moment we're just passing null. So if we fetch the report, that should be the actual act. The execute command should be part of the arrangement. And here we can change this out to actually assert based on the report. We should have cleaned one location. Okay, but we still don't have a reporter. So if we run this test now after small changes, and we failed, right? Because we're still generating the null report, null reporter report. Okay. Since we're passing null to our robot, and we have no real reporting class. Okay. Right. Let's check coordinate specification. We only really want in our reporter the number of unique places cleaned. Okay. So every time the robot moves, it needs to check if this is actually a new unique location. And obviously we need to store the locations where the robot actually has been. And initially we just want a method that works the simplest code possible. But eventually we really want a method that works well. So we need to use two sorts of tests. One test that checks that the system works at all. For example, if the robot moves to 5 unique locations, then it should report 5 as the locations. Then we have to define what we mean by running well, and really we're interested here in performance and efficiency, algorithmic efficiency. We want a method to store unique locations that the robot has cleaned, that is programmatically efficient, so that we can scale. If we switch from running 10 move commands to running 10,000 move commands, the system can handle that. With perhaps n log n efficiency. We don't want to see an exponential rise in execution time as we increase the number of movement commands. So really, yeah, n log n efficiency would be good. Linear efficiency, that would also be good. However, initially we just have to get our test to work, and so we have to give the robot some sort of memory so that every time it moves to a new location, it can actually compare this new location with the locations it's already visited, and on that basis decide whether or not it's going to add this new location to its list of unique locations. So we need to look at what possible solutions we can use to implement this. In our specification, it said we can think of the office as a grid. We know the grid has this grid has a defined boundary. In this case, minus 100,000 to plus 100,000, which is 200,000 wide, and it's the same as 200,000 tall. So we could create a 2D array, like for example, an integer array. Uh, 200,000 by 200,000. Which contains our cleaned locations. And initially, of course, every cell value will be 0, and every time we go to a new location, we can set the value of the array to 1. For example, if we've cleaned at location 5050, we set the value of the array at 5050 to 1. And after we've executed all the move commands, the number of locations, unique locations, would be the sum of the array, the sum of all the values. Or alternatively, we could use a Boolean array, where we set the cell's values to true, and then we just count the true values at the end of it. This is quite an efficient process. It's scalable, since well, the storage requirements are set. It's fixed. It doesn't matter how many commands move commands we run, and so we can easily handle good scalability, an increase in movement commands. So that's positive, and it would be linear programmatic efficiency, I think. Another solution is that we could describe our locations, clean locations, as a list of strings. And then we would need some sort of description. So for example, if we had a location which has got minus 5000x and y 7000, minus 7000, we could describe them as a comma separated string, or using some other symbol to celebrate, like a dollar or a ampersand, so to describe this actual location, something like this. And then we can store these unique descriptions in a list of strings. This would be a very, very simple implementation. And every time we move, we just check if the list contains our new location string description. and if it doesn't contain it, then we add it. And unfortunately, performance-wise, this would not be good, because as the list gets longer, it'll get slower and slower and slower, and so the performance of the system will degrade, probably in a non-linear fashion as well, which is bad, even worse. So our array solution is better in that regard. And in the list of strings, then the number of clean locations would just be the count variable on the string. Very simple. However, the list of strings probably can use less storage than the array solution. But and actually, I think the array solution will just use far too much memory. And our string list is just probably too slow, really, performance-wise. So a more likely alternative actually would probably be some sort of tree data structure, like perhaps a binary tree, for example, where each of the nodes contains coordinates, and then the sub nodes on the left or right, we split on the x values and even on the y values. That would be fairly efficient storage-wise, and we would achieve good algorithmic efficiency both in adding new coordinates and finding coordinates for that. Yep, that would actually work pretty well, although it'd be a little more complex to implement than either our array or the string. Now, if we look at the storage for a string, we can see that it's 2 to the 4 multiplied by 2 to the 5 multiplied by 2 to the 5, which is 4 to the 10. That's a lot of memory. It must be around 40 gigabytes or something, which is, I think it's beyond the capabilities of. Actually, well, we can quickly test this. It's worth giving it a shot, just for fun. See if we could. So if we create our Boolean, a two-dimensional array for our clean locations. And if we go in our constructor and we just try to instantiate, create a new an array which is 200,000 by 200,000. Yep, and then we can take one of the tests that use this form of the constructor. Actually, all of them use this form of the constructor. And for example, if we run this one, run the test, and see if we get a memory crash. And our test fails, and in fact there you can see we've got a system out of memory exception, as we suspected. It just uses far too much memory. So, unfortunate. That would have been simple and programmatically efficient, but we don't have the hardware. So we've either got a list or a tree. As usual, we should just implement the minimum changes in our code to get our test to work, and that would be the string list. So if we create a list of strings for their clean location strings, and then when the robot moves, we need to update the storage. We need to check if this new location, this new position, is already contained within the string list, the list of strings. For this, we're going to need some sort of string description for location that is unique for every unique location. And to do this, we can just override the locations toString method. And we're just going to encode in the x and y information. with some sort of separator symbol. Like for example here we're going to use the dollar, but we could use anything really. Probably not point or comma. So okay, now we have the string we need, and now we can do a quick check here whenever we move the robot to see if our list already contains this string description. Okay, yes. And if it doesn't contain the string, we just add it to we add the string to the string list. Okay, yep, the position to string. So that's updating. Right. That should work. And we need to update our reporter, so it needs the cleaned locations information. But let's just rerun our test and check and see if this works now. Okay, we get some failed tests. We're getting object reference not set. We haven't initialized, instantiated our cleaned location, our list. So we need to create our list. New uppit. Okay, let's rebuild F6 and run our tests again. See if we're doing better. We've got one failure. Okay, and here our move test is actually still failing. We're not reporting the correct report. Okay, our reporter is a null reporter. So we need to add a real reporter here. So let's create something which returns a new class, which returns an iReport interface. We don't want to use the test reporter here, so let's create a new reporter class, some sort of simple reporter class, yeah. And this reporter class is going to need access to the cleaned locations. Actually, we have a robot class here which is responsible for moving and changing position. But it also maintains an updated list of unique cleaned locations, which we only really need for reporting purposes. So now we're making changes in our robot class to improve reporting. And this breaks the single responsibility principle. Because really a class should only ever have one reason to change. And this class has at least two. So we should really transfer all this logic to do with clean locations, and we should move it to a reporting class, probably. That might improve things. So if we generate our simple reporter class, and we have to move it to the right assembly, and delete the other version in the wrong assembly. Let's clean up the namespace and make it public. So now the reporter class should have responsibility for the cleaned locations. So if we move our list string into here and implement the iReport interface. Okay, we have an example of our report in the specification documents. So if we just copy that across. gives the right format. We can just use a simple string format here. Right, we don't want to fall into the trap we had before, where we have null object reference for clean locations. Clean location strings, we want a real list. Okay, so we could add a constructor. No, we don't need to pass in anything. And here we can new up our list of strings. Yep. So just using resharper to clean up here, and now we can remove this from our robot class. And now we've got our reporter. We should we've made some changes. We should we need to pass the reporter to our robot class, and we need to move our new location handling. This logic needs to be carried out by the handled by the reporter class. So we need a new reporter method. Let's call yes, our reporter. So we call it report new method. No, report new position. Handle new position. No, that's not really a good name. It's too generic. Let's say register new position. And to this we would actually pass the position, which is being updated by the robot. Now we need to add this to our interface, which we can do through the generate, and implement in both our reporter classes. Now in the test reporter class, we don't actually need to do anything. So we can just leave that empty, although that is a breach of the Liskov's substitution principle, but we'll live with it here. So we just let it do nothing at the moment, and in our simple reporter class we'll actually do a proper implementation. Here we update our cleaned locations. So now we've separated our responsibilities between the robot class and the reporter class, which is a little bit better, even if we're still using a poor solution using a string list. So we're checking for our update of unique locations every time we move, so we can rerun our test now and see if we get a better result. So if we run our unit tests, and right, yes, and it succeeded. Which is good as far as it goes, but we know the solution is just not going to scale up. So we really need to come up with a better solution. And actually, first of all, we should create a test which tests for our minimum acceptable efficiency or performance, so that we can know a good solution when we find it. So that's our next job.